When circuit conductors are increased in size due to derating or voltage drop, the equipment grounding conductor, or EG, must also be increased proportionally. Let's walk through an example scenario and the calculations involved. Assume a 208 volts Y/120 volts, 3-phase, 4-wire feeder serving a 500 amps continuous nonlinear load. The standard overcurrent protective device, or OCPT, is rated at 700 amps. Assume you are using 90 degrees Celsius copper wire with 75 degrees Celsius terminals. The minimum conductor size for the load, considering the 75 degrees Celsius terminal rating, is 1500 mcm, which is good for 625 amps. However, with a current carrying neutral, you need to derate the 90 degrees Celsius ampacity of 705 amps for 4 conductors at 80%, resulting in a derated ampacity of 564 amps. To address this, the conductors are increased to 2 parallel 500 mcm conductors in 2 separate conduits. The total derated ampacity then becomes 688 amps, which is acceptable when using the next largest size overcurrent protective device. In this situation, the total ampacity has been increased, but the total circular mils, or cm, has decreased from 1,500,000 to 1 million. According to National Electrical Code Table 250.122, the required EGC size for a 700 amps overcurrent protective device is 1/0 copper. The question is, should the EGC be increased from this size, and if so, by what calculation? Yes, the size of the EGC needs to be increased. Here's how to calculate the necessary increase. Firstly, determine the cm increase in the circuit conductors. This is calculated as the initial cm minus the final cn. In our example, cm increase is 1,500,000 cm minus 1 million cm, which equals 500,000 cm. Secondly, determine the percentage increase in cm. This is calculated as the cm increase divided by the initial cm multiplied by 100%. In this case, the percentage increase is 500,000 cm divided by 1,500,000 cm multiplied by 100%, which equals 33.33%. Thirdly, increase the EGC size proportionally. This is calculated as the existing EGC size multiplied by 1 plus the percentage increase. Given that the existing EGC size is 1/0 copper, the increased EGC size is 1/0 copper multiplied by 1 plus 0.3333, which results in a 3/0 copper. Therefore, the EGC should be increased from 1/0 copper to 3/0 copper. This ensures the EGC is properly sized to provide adequate grounding protection, reflecting the increase in the overall conductor capacity of the circuit. It's important to remember that the increase in the EGC is directly related to the increase in the size of the ungrounded conductors. The calculation method ensures that the grounding path is appropriately sized to handle any potential fault current. The NEC requires this increase to maintain a low impedance ground fault path, which facilitates the operation of the overcurrent protective device and minimizes the risk of electrical shock. When working with parallel conductors, it is crucial to consider the combined ampacity and the corresponding increase in circular mils to ensure that the EGC is adequately sized. Overlooking this aspect can compromise the safety and effectiveness of the grounding system. By following the steps outlined above, you can accurately calculate the necessary increase in EGC size, ensuring compliance with the NEC and promoting safe electrical installation. Always consult the latest edition of the NEC and relevant local amendments for specific requirements and guidance. It is also advisable to seek the expertise of a qualified electrical engineer or inspector for complex installations or when in doubt about the correct sizing of conductors and grounding equipment. Remember that proper grounding is essential for electrical safety and the reliable operation of electrical equipment. When making these calculations, remember to adhere to the following principles to ensure accuracy and compliance with the electrical codes. Firstly, use the correct circular mil area for the initial and final conductor sizes. These values can be found in NEC Chapter 9, Table 8. Ensure that the values used are consistent with the conductor material, whether it is copper or aluminum, as the cm values differ. Secondly, accurately calculate the percentage increase. Double check your division and multiplication to confirm that the percentage increase is calculated correctly. Small errors in this step can lead to incorrect EGC sizing. Thirdly, select the appropriate EGC size based on the calculated increase. Use NEC Table 8 to determine the circular mill area of the increased EGC size. Verify that the increased EGC provides adequate protection for the circuit. Fourthly, consider the material of the EGC, copper or aluminum. The ampacity and circular mill values for copper and aluminum are different. Ensure that you use the correct values for the material being used in the installation. Fifthly, review the relevant NEC sections. Familiarize yourself with NEC sections 250.122, which covers equipment grounding, conductor sizing, and any other applicable sections related to conductor sizing and grounding requirements. Sixthly, consult with a qualified electrical engineer or inspector. If you are unsure about any aspect of the calculation or installation, seek guidance from a qualified professional. They can provide valuable insights and ensure that the installation complies with all applicable codes and standards. Seventhly, maintain thorough documentation. Keep detailed records of all calculations, conductor sizes, and grounding configurations. This documentation can be useful for future reference and for demonstrating compliance with the electrical codes. Eighthly, ensure proper installation practices. After calculating the correct EGC size, ensure that the installation is performed correctly. This includes proper termination of conductors, secure connections, and adherence to all applicable installation standards. Ninthly, verify the grounding system. After the installation is complete, verify the effectiveness of the grounding system through testing and inspection. This can help identify any potential issues and ensure that the system is functioning as intended. Tenthly, stay updated with code changes. The electrical codes are periodically updated to reflect new technologies and best practices. Stay informed about any changes to the NEC and other relevant codes to ensure that your installations comply with the latest requirements. By following these principles, you can ensure that you are accurately calculating the required increase in EGC size and that the electrical installation is safe and compliant with all applicable codes and standards. Proper grounding is essential for protecting people and equipment from electrical hazards. In the example we discussed, we assumed that the increase was solely due to derrating for the number of current-carrying conductors. However, if the increase is due to voltage drop, the same principles apply. Voltage drop calculations are typically performed to ensure that the voltage at the load remains within acceptable limits. When the voltage drop exceeds these limits, the conductor size must be increased. If the increase in conductor size is due to voltage drop, you still need to determine the percentage increase in circular mills and apply that percentage to the existing EGC size. This ensures that the EGC is sized appropriately for the increased conductor capacity, regardless of the reason for the increase. The NEC provides guidelines for calculating voltage drop and determining the appropriate conductor size to minimize voltage drop. Consult NEC section 215.2 AON for feeder conductors and 210.19 AON for branch circuit conductors. These sections recommend a maximum voltage drop of 3% for feeders and 5% for branch circuits. When performing voltage drop calculations, consider the length of the circuit, the load current, and the conductor impedance. Several online calculators and software tools can assist with these calculations. Remember that the goal is to select a conductor size that minimizes voltage drop while also complying with ampacity and overcurrent protection requirements. If the conductor size needs to be increased to meet voltage drop requirements, be sure to recalculate the EGC size accordingly. In some cases, it may be necessary to use larger conductors than initially planned to achieve both adequate voltage drop and proper grounding protection. Always prioritize safety and compliance with electrical codes when making these decisions. In addition to the calculations and considerations we have discussed, there are a few other important factors to keep in mind when sizing equipment grounding conductors. Firstly, consider the grounding electrode conductor. The grounding electrode conductor connects the grounding system to the earth. The size of the grounding electrode conductor is determined by EGC table 250.66 and is based on the size of the service entrance conductors. It is essential to ensure that the grounding electrode conductor is properly sized to provide a low impedance path to ground. Secondly, use proper grounding techniques. Proper grounding techniques are essential for ensuring the effectiveness of the grounding system. This includes using listed connectors, making secure connections, and avoiding ground loops. Ground loops can create unwanted current flow in the grounding system and can compromise its effectiveness. Thirdly, inspect and test the grounding system. Regularly inspect and test the grounding system to ensure that it is functioning properly. This includes checking the continuity of the grounding conductors, measuring the ground resistance, and verifying the integrity of the connections. Fourthly, follow manufacturer's instructions. Always follow the manufacturer's instructions when installing grounding equipment. This includes using the correct torque settings for connections and ensuring that the equipment is properly supported and protected. Fifthly, coordinate with other trades. Coordinate with other trades such as plumbers and HVAC technicians to ensure that the grounding system is properly integrated with other building systems. This can help avoid potential issues and ensure that the grounding system is effective. Sixthly, use surge protection devices. Surge protection devices can help protect sensitive electronic equipment from voltage surges and spikes. These devices should be properly grounded to ensure that they can effectively divert surge currents to ground. Seventhly, consider the environment. Consider the environment in which the grounding system is installed. In corrosive environments, it may be necessary to use corrosion-resistant materials to protect the grounding conductors and connections. Eighthly, document the grounding system. Maintain detailed records of the grounding system, including the size and type of conductors, the location of connections, and the results of inspections and tests. This documentation can be useful for future reference and for demonstrating compliance with electrical codes. Ninthly, provide training. Provide training to employees and contractors who work on the electrical system. This training should cover the importance of proper grounding and the procedures for inspecting and maintaining the grounding system. Tenthly, stay informed. Stay informed about changes to electrical codes and industry best practices related to grounding. This will help you ensure that your grounding system remains up to date and compliant with all applicable requirements. By considering these additional factors, you can enhance the effectiveness of the grounding system and ensure that it provides adequate protection against electrical hazards. Remember that proper grounding is a critical component of electrical safety and should be given careful attention. It is also important to note that the NEC provides specific requirements for the installation of equipment grounding conductors in different types of raceways and enclosures. For example, NEC section 250.130C requires that equipment grounding conductors be installed in the same raceway or cable as the circuit conductors. This ensures that the impedance of the grounding path is minimized and that ground faults can be quickly cleared. Similarly, NEC section 300.3b requires that all conductors of the same circuit, including the equipment grounding conductor, be installed in the same raceway or cable. This helps to reduce inductive reactance and minimize voltage drop. When installing equipment grounding conductors in metal raceways, it is essential to ensure that the raceway itself is properly bonded to the grounding system. This can be achieved by using listed bonding bushings or other approved methods. The goal is to create a continuous, low-impedance path to ground that can effectively carry fault currents. In addition to the general requirements for equipment grounding conductors, there are also specific rules for certain types of equipment and installations. For example, NEC section 250.118 lists the acceptable types of equipment grounding conductors, which include wire, metal raceways, and other approved means. Similarly, NEC section 250.146 provides requirements for grounding equipment connected by cord and plug. These requirements are designed to ensure that portable equipment is properly grounded, even when it is not permanently connected to the building's wiring system. When working with sensitive electronic equipment, it may be necessary to use isolated grounding techniques to minimize noise and interference. Isolated grounding involves separating the equipment grounding conductor from the building's grounding system and connecting it directly to the grounding electrode. This can help to reduce ground loops and improve the performance of sensitive equipment. However, isolated grounding should only be used in accordance with the NEC and under the supervision of a qualified electrical engineer. Another important consideration when sizing equipment grounding conductors is the potential for future expansion or modifications to the electrical system. It is often prudent to oversize the equipment grounding conductors to accommodate future increases in load or changes to the wiring system. This can help to avoid the need for costly and time-consuming upgrades in the future. When making changes to an existing electrical system, it is essential to review the entire grounding system to ensure that it remains adequate and compliant with current codes. This includes checking the size of the equipment grounding conductors, the integrity of the connections, and the effectiveness of the grounding electrodes. By taking a comprehensive approach to grounding, you can ensure that the electrical system remains safe and reliable for years to come. Finally, it is important to remember that the NEC is not a substitute for sound engineering judgment. The NEC provides minimum requirements for electrical installations, but it is up to the designer and installer to ensure that the system is safe and suitable for its intended use. This includes considering factors such as the environment, the type of equipment being served, and the potential for future changes to the system. By exercising sound engineering judgment and following the guidelines of the NEC, you can create an electrical system that is both safe and reliable. The process of increasing the equipment grounding conductor size based on an increase in the circuit conductor size is a critical aspect of electrical safety and code compliance. The calculations and considerations discussed above provide a comprehensive guide to understanding and implementing these requirements. By following these guidelines, you can ensure that the electrical system is properly grounded and that potential hazards are minimized. Remember to always consult the latest edition of the NEC and to seek the guidance of a qualified electrical professional when necessary. This combined approach ensures the highest degree of safety and reliability in electrical installations.